All right, today we're going to talk about least squares. This is where linear algebra really starts to shine in terms of its applications. So we're just going to dive into a nice, simple, perhaps a little contrived example, but at least you'll be able to see where this can go. So suppose you're selling apples, say, and you can think of this as we're building some coordinates x, y. So if you sell one apple one day, you might make $3. And the next day you might make 0. And of course, you'll make $0. And on the last day, the third day, you sell an apple, but you lost the money or you gave it away for free, so you made $0. And what we want to be able to do is, given any data set, we want to be able to figure out what is the line that predicts how much. If we were to expand our business and sell 100 apples, how much money will we make? Right? That might be a little silly here because the data size is kind of small, but we'll still be able to use the same mathematical techniques to get a good guess at what that answer should be. All right, so if we plot these data points, we're going to have these three guys. And the goal that we want to be able to do is to find the best line. And there's some notion of best that's underlying all this. There could be multiple notions of best, and we're going to pick one of them. But for now, let's just eyeball what we think the best line is. So I think maybe it might kind of look like this. And that kind of looks like just y equals x. I just kind of eyeballed it. So we're going to see if I'm right. We don't know if that's exactly what we want, but we want to be able to construct a mathematically consistent method to find the best line. And just kind of a heads up of where this is going, right? Since we're dealing with linear algebra and we have lines and planes and hyperplanes, it's the same idea. We want to be able to generalize this idea into much more abstract spaces. If you have a whole bunch of data, more than just 2 columns of data, right? You also want to be able to build that a linear model that can model that data. So it's not just the best line, but also the best plane or best hyperplane that gets you to predict that data. All right, so if we lived in a perfect world and you never got bad data, everything always lied on that line. So if it was perfect, what would end up happening? Well, we would have y equals mx plus b. So this is just the general form of the model that we want to fit. And now we're going to plug in the x and the y into here. So we have, for the first equation, we have that 3 equals m times 1 plus b. 0 equals m plus 0 plus b. And for the last one, we have 0 equals m times 1 plus b. And this may seem a little weird, but we now see that we can kind of see that this is a vector matrix equation. In fact, we can write this. On the left, we have 3, 0, 0. And on the right, we really have 1, 0, 1, 1, 1, 1 times MB. In fact, if we multiply this out, the M's kind of correspond to the first column and those B's correspond to the second column. And so that's why we have this vector matrix equation. We also know that this is going to be bogus. So if we look right here at this top line right here, what does that mean? This says that 3 has to be equal to M plus B. And this bottom one here says that 0 has to equal M plus B. So this is bogus. So one other way of rewriting our goal is not just to be able to find the best line or plane or hyperplane, but be able to find the best solution for any inconsistent system. And in fact, finding the equation of a line is one application of finding the best solution to an inconsistent system. But this right here is kind of what we really want to be able to do. We're going to look at this problem of finding the best line as how can we find the best solution when there isn't any solution? What's the best solution? So here we have, we're going to kind of write this slightly differently. So this is going to be AX equals B. And we want to be able to find a solution for X, even when there isn't really any solution. We want to find the best non-solution. All right, so what's the punchline? Let's just jump right to the punchline right now. So the punchline for all of this is that if AX equals B is inconsistent, then the best solution, meaning the least squares solution, later we'll talk about what we really mean by least squares, but for now it's just a little bit of a mystery, is the solution to A transpose AX equals A transpose B. So in some sense, if you have, what this punchline really says is if you have an inconsistent system, you can't solve it exactly, but you want the best guess at what the solution should be if there was a solution, all you have to do is you're going to multiply both sides by A transpose and then solve this system. And so this seems kind of magical, but what part of the properties of the image in the kernel of a matrix is that when you perform this operation by multiplying by A transpose, you're always going to be guaranteed a solution. You may get more than one still, but you're going to guarantee yourself there's a solution. And we'll get to why that's the case later. But let's just put this punchline into practice. So let's just try it. So beforehand, we had our A was this matrix. Our X was our M and our B. And the vector on the right was 3, 0, 0. All right, so this right here is our A. This is our B. And what the punchline says is we should just multiply this by A transpose. So we should just do A transpose. There we go. So now we have this. Now, this is going to seem kind of magical that I'm saying if we multiply by A transpose, we're going to be guaranteed at least one solution, and that will be the best solution. But let's just try it to make sure everything is consistent. All right, so here on the left, if we multiply this, right, rows by columns, we're going to get 2, 2, 2, and 3 times MB equals, and here we have rows by columns again. So we have 3 and 3. So altogether we have this matrix vector equation. And we just have to solve this to find our best fit. All right, so what's going to end up happening here is we have this augmented matrix. So now we're just solving. All right, I have a nice pivot position right here. So we're going to divide by half. And then we're going to subtract. We're going to go ahead and subtract that second row. Oh, we're not there yet. And now we just need to get rid of this pesky one right here. So here we have our system. And so this says, this top one here says that M, the best solution for M is 3/2. And this bottom one here says the best solution for B is B equals 0. So this is your best solution to our problem. Right. So this says, now if we go back here, this says the slope is 3/2 and the y-intercept is 0. So the best line that we should have had was actually something more like maybe a little steeper than what we had before. Right. But you'll notice that it still passes the eyeball test, but now we did it in a mathematically consistent way. So this is the best way, that's the best line that fits this data. And the key to the punchline is whenever you want to do that, you're just going to multiply both sides of your equation by A transpose and then solve it that way. All right, so let's do this in a slightly different way from a different geometric perspective, just to see that all the linear algebra is consistent. So that's kind of what we did was how you actually do it. But now I want to do two extra examples using the same data to demonstrate that this is in fact consistent with the math, with all the math that we've learned. All right, so one thing that may seem kind of strange here is when we consider this equation, this is going to be really weird when you see it, is that this is really an R3. So the problem we posed originally, right? The problem we posed with a line, this is an R2. There's nothing R3 about this problem at all. It's all in R2. But now we're going to go to R3 because I want you to see that in fact, this is really applying the geometric properties of the subspaces of the image and the kernel. All right, so this is inconsistent because 300 is not in the image of A. So it's not in the image of A. One way to see that is because the image of A is just the span of the columns. So there's no way to get 300 because all the columns have the same X and Z values. There's no way to get differing X and Z values, but the 300 has a different X and Z value. So of course, there's not going to be any way whatsoever to create 300 using these two vectors. So if we draw these vectors in R3, so this first one will be 1, 1, 1, 0. So it might look something like this. And the second vector, let's put this one in green. This one's going to come kind of almost straight at us. This is coming like straight at us. And those two vectors, that plane, which might look something like this right here. So it's kind of going downwards in the plane. It goes through the origin. That's kind of going down. That plane is now the image of A. That's the image of A. So those are two vectors that created the image of A. And in some sense, what the problem of finding the best fit is in some sense saying, okay, what's the vector in the image of A that best approximates that vector? So we want 300. So 300, where's 300? This is the x-axis. So 300 is kind of like all the way out here. And now what we're going to do is we want to ask this, okay, how do we best approximate 300 as a combination of these two vectors? What's the best way, what's the closest thing we can get to of getting 300? So the question we now want to ask is, what is the best approximation of B, or in this case, 300, as a combination of the columns of A? So in this case, that's 101 and 111. And so the best approximation is going to be the projection, right? So we want to find out what point. So maybe it's like this point right here, because it's whatever the projection is. We want to project this guy straight down. And so the best approximation might be this guy. So the best approximation will be that highlighted vector. I don't know what that vector is. That seems to be about a little bit in the X. It's not on the, it's kind of on the Y. It's not in, it's above the X axis, but not in any of the Y directions. So I would say that's probably about maybe 202 or something, just geometrically. That seems like 202. And this is going to correspond to our solution that we found before. Now, this may not seem very obvious. Maybe 202 is not quite right. We kind of already know what the answer is. So maybe it's actually like 3 halves in the X and 3 halves in the Z and 0 in the Y. right? So it's just the highlighted part, not the projected part. So when you project X down into that purple plane in the image of A, you get a vector that's basically 3/2, 0, 3/2. Right? And why does this all come into play? Well, keep in mind, what are these two vectors here? These two vectors that we have, this one corresponds to M, and the second one is the one that corresponds to B. And so what this is saying is that if this is equal to 3/2, 0, 3/2, how do we get that? Well, that means that we had to use 3/2 for M and 0 for B to get this vector. And this is now consistent. So in some sense, the coordinates of the vector in using the basis of the columns, using our data, is going to give us what the M and the B are. That's how we got M and B. So this is another way of interpreting what's actually going on in the context of linear algebra. All right, so let's just dive into why this actually works and why it's called least squares. And then we'll call it a day. So why does this work? So what we're really doing is we want to find the least squares. And so the goal from before, when we find the least squares to an inconsistent question, we want to find the best solution to an inconsistent system. So that was our goal, but that's kind of vague mathematically. So we're going to actually put this in more mathematical context. The goal is going to be to minimize the distance between B and the image of A. So this is kind of vague, right? But more concretely, we want to minimize over all vectors in the image of A of B minus Y. So in the context of what we did above, right, we're given this vector B. This was like our vector B right here. This was like our 3, 0, 0. And the Y that we found, the closest Y that we found was that one. That's how we're framing this. We want to find the best vector in the image of A. Now, the key thing is, what does it really mean to be the image of A? Being in the image of A means that Y equals AX for some X. That's what it means to be in the image. You're an output for some X. So we can actually write this instead. We can write this as we want to minimize the norm of B minus A times X over all possible X. That's our goal. All right, so where does the name least squares come into play? Well, keep in mind that this, the norm of a vector, is just equal to the square root of the sum of the components. And in fact, the minimization of that is the same thing as minimizing the square. So the square is just minimizing this. So the name least squares comes into play that when you're minimizing this, minimizing the norm is the same thing as minimizing a square. So that's where the name least squares comes into play. So just a recap, we're trying to minimize the distance between some hyperplane and our vector. And that's just minimizing some sum of squares. That's why we call it least squares. All right. So now this, intuitively, we know that the best solution to this is going to be the projection of B onto the image of A. That's kind of the intuitive solution. Is you just project it on there and then you choose the X that achieves that. So just to go back up to here to our picture from before, right? If you want to find the closest solution, right? All you have to do is figure out, okay, how does B project onto the image? And then instead of using this B, you're going to use this Y in some sense. You're going to use the projected version of B. So now, if we want to solve this equation, instead of solving AX equals B, we're going to solve AX equals, say, B perpendicular. This is just a projection. And since B lives in the image now, since B parallel, the projection lives in the image, this has a solution. All right, now this is where kind of the magic comes into play. What we're going to do, and this really leverages the things that we've done over the last couple of sessions, is we're going to multiply both sides by A transpose. And we can do this for free. This is just algebra. You're allowed to just multiply the same thing on both sides. But now this is kind of why this all works, really comes down to understanding the kernel and the image. So the next step to see why we can use our punchline, where does this punchline come from, is that we can add A transpose times B perpendicular. And where this comes from on this side, this is actually equal to 0. That's equal to the 0 vector. And this is equal to 0 because B perpendicular, by definition of perpendicular, is perpendicular to the image of A, but the kernel of A transpose, we did this last time, is equal to the image of A perpendicular. So this says that if B perpendicular is by necessarily in here, B perpendicular lives in this set right here. So it also has to live in here, which means it's in the kernel, which means when you multiply it by A transpose, it gets annihilated to 0. That's what the kernel means. So we're going to add 0 to both sides, but on one side, we're going to do it in this funny way. We're going to multiply by A transpose B perpendicular. And now this is where the punchline comes from. So on one side, we have A transpose AX, and on the other side, we have A transpose B parallel plus A transpose B perpendicular. And then we can factor out that A transpose. And on the right, we end up with A transpose B. So this is our punchline that we had. So that's why it actually works. All right, so this works. We kind of went through it geometrically here to demonstrate that it works. We did this geometrically one more time using kind of the image and the kernel with those raw numbers. And we did it algebraically with just using our punchline from the get-go to be able to get the solution. And so that's really about how least squares works, why it's called least squares, and why it actually works.